DePiro, and this video is about mesh current analysis. After this video, you'll be able to perform an initial version of a mesh current analysis that involves voltage sources. You'll also be able to relate mesh currents to the true currents of a given element. Prereqs are only Ohm's law, passive sign convention, and Kirchhoff's voltage law. So why do we need this method? Well, not all circuits can be analyzed via an equivalent that involves series parallel combinations. Can you think of a change to this circuit that would eliminate the option to simplify it down via series parallel combos? That's an example. There are some limitations to this technique. In this case, circuits must be planar with mesh current analysis. That means that you can draw the circuit on a piece of paper without any overlapping wires. It's a very useful method because it handles arbitrarily large circuits. It's systematic, that is, it uses the same procedure for any circuit. And it yields equations that are guaranteed to be solvable, n independent equations with n unknowns. This is an alternative to node voltage analysis, and in comparison, mesh analysis works well when we have lots of voltage sources. Okay, so how does this work? Well, we're going to do KVL on each mesh, and that'll yield n equations. The unknowns are the currents going around each mesh. We decompose a complex circuit into meshes in order to establish well-defined criteria for each equation. Now, we have an issue because circuits can have complicated patterns of current flow. And it'd be very nice to have a current that's specific to a mesh to use with KVL. Imagine when we had just a single mesh and a single KVL equation. The current was it was obvious, it was clear. It was just that one current circulating around that one mesh. So we do have an issue here for more complicated circuits. So what we do is we define theoretical currents that circulate around each mesh. These are the quote-unquote mesh currents. Yes, theoretical flows of current. Okay, we got to talk about this. So what are these mesh currents? Well, they differ from real physical currents, and let's examine the differences. Here you see an example, simple circuit, and the currents that are shown here are real currents, 5 up, 5 over, 4 down, 1 across, and so forth. Mesh currents theoretically circulate around only one mesh. So here's mesh current I1. The indication here is that, designation here is showing that it's circulating in the clockwise direction. Here's mesh current I2. And with these theoretical currents, it is as if the electrons are partitioned to stay in their respective mesh, as if the electrons associated with mesh 1 are only circulating around in this mesh. And that's separate from the electrons circulating around in mesh 2. This is a theoretical decomposition. Now we choose to define mesh currents in a particular direction, and textbooks often use clockwise. I'll always use clockwise. And another thing to point out here is note that we can have more than one mesh current passing through a given element. This vertical resistor here that's on the shared branch has 2 mesh currents going through it. Furthermore, they are flowing in different directions. Okay, so let's talk about the relationship between real currents and mesh currents. We can express them in terms of each other using simple algebraic relationships or direct relationships. Let's talk about this current IA, this true current IA that's going up through the source. How would it relate to the mesh currents? Very simply, IA is equal to I1. How about this current IB, true current IB going down through this resistor on the right-hand side? That would be equal to I2. And how about this current? A true current, IC, flowing vertically down through that shared resistor. IC would equal what? That is I1 minus I2. IC and I1 are going in the same direction through that vertical element. I2 is going against it. Okay, so how can this technique work if we don't solve for the real currents, which is what we're really after at the end of the day? Well, the real currents and the mesh currents are related algebraically as a linear combination. That's why we can solve for the mesh currents and ultimately reveal the true currents, the real currents. Now, a couple notes that you'll see come into play. When we're using Ohm's law, we must use real currents. Those will be expressed in terms of our unknowns, which are the mesh currents. We must also obey passive sign convention to ensure conservation of energy, and this graphic here illustrates passive sign. Here's the initial version of our mesh current analysis algorithm, and this will work fine with voltage sources. Define the currents around each mesh. I'll choose clockwise. We then choose to apply KVL clockwise. A number of these steps will be familiar to you, thinking back to Kirchhoff's voltage law, KVL. Then we must use passive sign to assign polarities. That's a must. Must use true currents with Ohm's law. Ohm's law doesn't care about this silly partitioning. It needs the true current. We then have a choice about how we add or subtract terms as we're going around the mesh and forming our KVL equation. Then we solve. Again, note some of the choices are mandatory with the must, some are optional with the choice. Choose. And I always make consistent choices. That's Mr. Monk. This helps me avoid calculation errors. Yeah. Okay, so starting off here, we'll go through an example, and we're going to define currents around each mesh. Monk chooses clockwise. That's the way these are in the diagram. Those are our unknowns we'll solve for. Next, we'll also apply KVL going in a clockwise direction. For example, following the direction of I1 when we're over here in mesh 1. We use passive sign, use true currents with Ohm's law, and we'll choose to add in a term if we hit the plus polarity first, subtract off a term if we hit the minus polarity first. Okay, so Monk's style starts at 7 o'clock, and here we go. Down here at 7 o'clock, following the direction of I1, I come up to this voltage source and hit the minus sign, the minus side of the source first. So I'm going to subtract off the value of the source, starting with minus 45 in my first mesh. Following around in the direction of mesh current I1, I'm using passive sign convention to assign a polarity for this horizontal resistor here. So I put the plus designation there, and I'm going to add in that term 5 times the mesh current I1. I1 is the true current flowing through here. Continuing on around, again, passive sign tells me to put the plus sign as I'm entering this resistor. I then need to use the true current downward in order to properly compute Ohm's law. So I want the true current downward through this 5 ohm resistor, and in this case it would be I1 minus I2. I1 is flowing downward, I2 is flowing upward. So it's I1 minus I2, and that completes my first mesh. Okay, KVL2, again, starting at 7 o'clock. By passive sign convention, I assign the plus sign to the bottom side of this resistor here. Then I need to get the true current upward for Ohm's law, and in this case, the true current upward is going to be I2 minus I1. So I have 5 times I2 minus I1. Continuing around by passive sign, I move my current's going from left to right. So I put the plus sign to the left, and I then add in my next term. So I'm going to say plus 1 times I2. I2, the mesh current I2, is the true current through that resistor. Similarly, for the remaining terms associated with the second mesh, there is just that single current I2. Simplifying the algebra, we have this. Solving gives us 5 amps for I1, 1 amp for I2. Okay. Now let's relate those results to our true currents. And so based on those results, let's talk about what the true current is through this resistor R7. Notice both I1 and I2 contribute. Since I1 is the larger value, 5, that means that the total current is going to be 4 amps downward, okay, because we have 5 minus 1 going up. Total current through this vertical resistor here is 4 amps in the downward direction. True voltage, okay, we need to look to passive sign convention to make sure we get the polarity right. Since the true current is downward, we know that the true voltage polarity would have a plus sign on the top. Okay, that means in this case we have 20 volts, 4 times the 5 ohm resistor, plus sign at the top. Okay, so once again, here is our procedure. This will work perfectly well when we just have voltage sources in a circuit. And now you should be able to, with a little practice, perform a mesh analysis on circuits with voltage sources and be able to relate mesh currents to the true currents of a given element.